so I hope that all of you were able to take the quiz number today and were able to submit the last one. You can draw your structure. It's the same method for the problem set that we haven't already submitted your problem set number 1. That's how you will submit your files for your problem set. You will upload it or you will send the link, but make sure that the link that is submitted is there for at least this whole semester, just in case. So I can access it, and make sure that when you send the link, it's copy the link in one with the link, paste it, copy in one with the link, paste it indicated slide. So what I did for the quiz is, or what was given for the quiz now, is for me to check your background in organic chemistry. For more on the structure writing for the stereoisomers, particularly the chapter 8, carbohydrates, so you will have to learn more of that in the problem set. So I will give them a problem set for you to know the stereoisomers, all the possible stereoisomers, knowing the chiral centers, as what you have learned from that. Of course, you will have to apply that in proteins. So last meeting we talked about carbohydrates, and we learned about the structures of the carbohydrates. We learned that there are functional groups that you can see carbohydrates, right? You will have there are two kinds of the carbohydrates where you have the aldehyde functional group or where you have your ketone. Okay, but so far what we had introduced is the one with the aldehyde. So we call it one as aldoses, and the number of carbons that we have in our carbohydrates, monosaccharide in particular, is 3. Okay, it's aldehyde for the aldehydes. Okay, of course, expect that there is a chiral center for that, and what we've learned in organic chemistry is that having the chiral center, there are different stereoisomers that actually can be made with the formula 2 to the n, where n is the number of chiral centers. You learned that in organic chemistry. So here you have one chiral center. You expect these 2 stereoisomers possible. Here you have 2 chiral centers. You expect 4 chiral centers possible. But what is drawn here is only 2 stereoisomers. There's another 2 for it to have 4 stereoisomers. And of course, I don't have to go back to organic chemistry, but we should review on what we have stereochemistry. You can go to your portals, organic chemistry. I think so fresh, same part, but it's the last semester. You should be able to remember this one. Okay, so what we had introduced last meeting again is the aldehyde-containing sugars. So you have 3, 4, 5, 6 carbon-containing sugars. You have the aldose, triose, tetrose, pentose, and hexose. And what we have learned is that all the stereochemistry in the carbohydrates is based from D-glyceraldehyde. The D-glyceraldehyde, when you have this structure, when your OH is on the right side of this Fisher projection. If you draw this one here, this Fisher projection, the OH is on the right side. So when you draw or increase on the number of carbons, you always have to look on the OH, the one that is far from the aldehyde or carbonate carbon. So let's say here, we have to look at this one, the OH is always to the right. So that's the reference for you that this all are in the D position. Is the D the one where it's the designation for the monosaccharide? We don't use the R and S that we have read in organic chemistry. So the D-glyceraldehyde, it's referred to this one. So all the rest of the monosaccharides referred as D. And the OH is on the right side. No? And we learned for this Fisher projection is that this is oriented towards you, and the vertical, this one, the aldehyde C double bond O hydrogen here. The vertical is oriented away from you. You have the broken line here, and this one, the horizontal line, this one, HOH, is oriented towards you. Whenever you see again the structures of the monosaccharides, it is meant to be that way. All you have structure like this, all in the vertical position are oriented away from you. And this in the horizontal are oriented towards you. Okay, and you have this one oriented towards you, and the OH is on the right side of this one, this position, and all the rest here. When you have the OH on the right side, the farthest OH from the carbon-carbon, it means that you are in the D designation. Okay, that's what we use. If the OH is on the left, you have the L designation of your monosaccharide. So it's reference from D-glyceraldehyde. You have it. Okay. And you've learned also what epimers are. Epimers are when you have the same orientations, the same structures of all the hydroxy group in your monosaccharide, but they differ only in one position. Of course, in your organic chemistry, you've learned what are enantiomers. Enantiomers are simply mirror image of your chiral compound. So, and the mirror image of that superposable neutral. And we learned also there's another kind of sugar, which is the ketose, wherein you will find a ketone in the structure like this one. So the simplest ketose is 3 carbon atom ketose, but this is not a chiral ketone. We will have the first chiral ketose rather to be made of 4 carbon. All this one is D-added. And then you can have 5 carbon, 6 carbon sugar. Again, the reference of the D is when you have your OH on the right side away, the OH that is the farthest away from the carbonyl carbon. You don't have an aldehyde here like C double bond O hydrogen, but you will get the C double bond O. This is a first you have your carbon here and you have C double bond O, C double bond O. You don't have a hydrogen. It's a hydrogen that is already an aldehyde. Again, there is 2 kinds of sugars, monosaccharide, the one with the ketose and the one with the aldehyde. So here we are talking of the ketose. Our glucose is made up of an aldehyde. There's an aldehyde there, and the rest are hydroxyl group or the alcohol group. Okay. So for the ketose, what are the common sugar that we have for the ketose? The common, I think, that you know is the fructose. The fructose one that you can find in the fruits. Some of these are, I think it's a value added to some of the foods that we take. Okay, so again, these are examples of the ketone-containing sugars. And always have to be mindful of whether the OH is written on the right or on the left, because each carbon is a chiral carbon. It's a chiral center here. The carbon is connected to 4 different group of atoms. So this on the horizontal is oriented towards you. So any interchange of this hydrogen and oxygen, hydroxyl group OH, will lead to a different kind of stereoisomer or a different kind of sugar. So this is the hierarchy of how you will have to add your sugar or your carbon rather. You start with the one from the carbonyl carbon, single bond O. Okay. Always have to know your reference OH is on the right, for it to be called again the D sugar. Okay, so you have your D, you add your carbon after your single bond O, you have your carbon, and your OH can be positioned to the right or to the left. Okay, so it's still a D because your OH, the one that's pink here, is the one that is farthest from the carbonyl carbon is located to the right side. Okay, oriented towards you, located on the right side. So this is referenced as D sugar. And there is an amino sugar also, another kind where one of the OH is replaced with an H2. So we call this one as amino. For example, you have your glucose instead of the glucose ribitro, 1, 2, 3, 4, 5, 6, or 6 carbon sugar for glucose, and you have your OH, OH, OH on the right side, and the other is on the left. So 1, 2, 3, 4 chiral centers for the glucose. But if one of the OH here, this side is altered to amine group, so you have here the glucosamine. Glucosamine, the lactosamine. If one again of the OH is finished. So that ends the discussion last time. So now we'll talk about the physical properties of the monosaccharides. Monosaccharides are colorless crystalline solids. Of course, if you leave when you have your sugar, they are actually the pure one. They are actually colorless and they are solid crystal. And you see that in the structure of the monosaccharides, there's a lot of OH. So it's possible for them to do hydrogen bonding formation and even with water. So because hydrogen bonding is possible between the polar groups OH and water, of course your water is H2O. All monosaccharides are very soluble in water. They are only slightly soluble in ethanol and are insoluble in nonpolar solvents, diethyl ether or any nonpolar solvents. But basically, they are soluble in water. It's easy to dissolve them. It's slightly soluble in sugars. Before we do on how the reactions of the cyclic structures of the monosaccharides, let's review first on one of the reactions that I'm not sure if you have discussed this in organic chemistry. So one of the reactions actually of the alcohols and the aldehyde is what we call as the hemiacetal formation. So in here you will have your alcohol where there is an electrons here, same oxygen, will be used, the electrons will be used to form a bond with carbon here. Carbon being a partially positive atom because there is an oxygen here. Oxygen being an electronegative atom will become partially negative. Okay, this side here is oxygen. And carbon is partially positive because oxygen being an electronegative atom is brought electrons down. So it will leave carbon with slightly partial positive. So when you have an alcohol, if you remember your Lewis structures, your alcohol or your OH, oxygen will always have two bonds, two covalent bonds. So one for the R, another carbon here, and another one for the hydrogen. And there is two lone pairs in oxygen of the holiday octet. So when you have your alcohol with your OH, we use an electron pair to form a bond. Sure we have discussed that it's a Lewis atom and a Lewis base. So use the electron pair to form a bond of partially positive carbon. To have that one, your oxygen will abstract a proton from the solution to have your OH, and then you will have your OR here. OR, the hydrogen of your OR. So once you have this, you have your OR and OH. So from the aldehyde, you form an alcohol, and from alcohol here, you form like a ketone, an ether, rather, COR, CO, another carbon, COR. This is what we call as the hemiacetal. When you have your OR and OH, you form one as a hemiacetal. And when you have another alcohol, okay, we replace this OH, the same reaction. When you have another OH, OR, or another alcohol, you get an OR, OR, two OR. You call this one as acetal. Okay, so an aldehyde and alcohol reacting with each other, you actually form a hemiacetal first, where you will get one OR, and an acetal where you get two OR. Again, what is an R? An R is any alkyl groups. Okay, you have a ketone and an alcohol. This one is an aldehyde. Right? You have a ketone. A ketone is when you have C double bond O and the carbon here. And then the double bond O is connected to carbon and another carbon, alkyl alkene. For an aldehyde, you have your C-double bond O, one of the carbons, or one of the groups bonded to carbon is an R, or carbon atom, and another is hydrogen. It's an aldehyde. For a ketone is an R. Now, when a ketone is close to an alcohol, now they can actually react. Similar to this, you actually form a hemi-ketone formation. We get an OH and an OR. So the O here, with its electron, will attack this partially positive carbon, and the O here will attack another hydrogen from the solution. You'll get an OH and you get an OR. But since your carbon here, carbonyl carbon is connected to 2R, you call this one as a hemi-ketone. When the other is bonded to R and hydrogen, so you get your OH and R, you call this one as hemi-acetal. And once you replace the OH with another alcohol to get your OR, you have your ketone. Here you have your acetal. But the common thing with them is you have your OR. The only difference is that one is a hydrogen, the other is both R. See here the hemi-acetal and the hemi-ketone, you have the OH and the OR, OH and the OR. And the difference is the R, the hydrogen here, attached to the carbonyl carbon. Okay, so this is the common reaction when you have an aldehyde and an alcohol. Now imagine for your monosaccharides, you have an aldehyde in one structure, you have an aldehyde, and of course you have an alcohol. You have, for a ketose, you have a ketone in one structure and you have an alcohol in one structure. So you can imagine that it's possible for our monosaccharide actually to undergo this kind of reaction. In fact, monosaccharides can actually do hemi-acetal formation or hemi-ketone formation. Okay. So, for example, you have here your 1, 2, 3, 4, 5 carbon, 1, 2, 3, 4, 5 carbon atoms, and the fourth carbon, it's a steric-center, it's bonded to 4 different group of atoms. You have the OH, you have the methyl, you have this group, and the last one is the hydrogen. Okay, and then you have your C-double bond O hydrogen. This is an aldehyde. So they can actually react. This is like an alcohol. It can actually react here. For this to react, you actually contain this one. Let's get this to be close contact with each other. This is like an alcohol. This is like an aldehyde. So your O can actually attack the partially positive carbon here, carbon number 1. And the O here, oxygen, will use this bond to bond with hydrogen to get your OH here. Okay, so you get your, and then this one is removed, you get your OR, and then you have your OH. Okay, you have your OR and you have your OH. But in this case, this is actually a cyclic one. Because we started with aldehyde, we have a hemi-acetal formation. So this is the common cyclic reactions with the monosaccharide, and they will actually react within its molecule to form a hemi-acetal in the case of an aldose. So the new carbon steric center created in forming structure is what we call as an anomeric carbon. We have here an anomeric carbon. And stereoisomers that differ in configuration only by anomeric carbon are called anomers. Okay, so let's have a focus on the glucose first. The glucose, which is an aldehyde. Okay, you have your CHO. CHO is a shortcut for C-double bond O and hydrogen. Always remember carbon should always have 4 bonds. Okay. So this is the structure of the D-glucose, and you can redraw this structure in such a way that the OH is close to the C-double bond. So you have the fifth carbon, starting from carbonyl carbon, C-double bond O carbon, or you call it one carbon. And close to that, okay, for them to react. So you have 1, 2, 3, 4, 5. The sixth one is not involved in the reaction, but the fifth carbon can involve to form a 6-membered ring actually. So what happens here is that this is a planar structure, single bond hydrogen. It's a trigonal planar. Whenever you have carbon or any atom bonded to three atoms lang, you have your carbon bonded to oxygen, hydrogen, and another carbon. So its geometry is planar. So which means that when you have your electrons coming from the oxygen here of OH, will attack at the top, sa top, or it will attack sa bottom, sa ilalim. Okay. So when it attacks sa bottom, sa ibabaw, no, what happens is that we'll have here an alpha, okay, top or bottom, or you can have your beta. So which means that you will get your O carbon, you form a bond, O and carbon, and then the O will get, well, abstract a hydrogen, not to form an OH. So here, your OH can either be up or it can either be down. Okay, so you call this carbon now to be anomeric carbon. An anomeric carbon is the new carbon steric center created in forming the cyclic structure. So this one, katong si carbonyl carbon kaganina, mahimo siyang anomeric carbon. The new steric center no, that is created when the OH and the C double bond O hydrogen reacts. Okay, so your anomeric carbon, to say mag-differ where you can get our cyclic structure. Okay, since you will have this one, the first one is the beta D-glucose. It's still a D-glucose in a cyclic structure. The other one is also a glucose in a cyclic form, but the first one is called beta. Okay, when it's oriented, when you have this position, it's oriented up on the same, it's carbon 5 that reacts, no? It's carbon 5 that reacts. So you will have your beta D-glucose. So you have this up, down, you have this up, down, this becomes our carbon 1. Okay, so you have here the beta D-glucose, and you have the down, up, down for the OH, and you have an alpha D-glucose. All this one is anomeric. So this one is still a glucose, no? But what we have seen here is the cyclic form of the glucose, because they will self-react. The OH and the CHO will self-react to form the cyclic form of the glucose. So in it's already early. Okay, so in other words, for those monosaccharides, now they can self-react with each other to form the cyclic form of its structure. Now the cyclic form, we call this one as the Haworth projection. So you have this. You just have to be familiar of how the glucose are. So you have your second carbon, it's down, up, down, down, up, down. You have here from this, you have on the right comes down. In carbon 2, no, this is our carbon 2. You have down, up, down, up, down. Of course, you have the fifth carbon is the one to use cyclic form here. This is the sixth. We have here. And the anomeric carbon can either be a beta if it's written up, or an alpha it's written down with this one. Okay. So in naming of cyclic monosaccharides, a 6-membered hemiacetal, what we have in here is the hemiacetal. When you say hemiacetal, you have an OR, O with carbon here, you call it an OR, and an OH, this carbon, you call that, and this carbon has a hydrogen, okay, call this one as a hemiacetal, but in cyclic form. A 6-membered hemiacetal ring is indicated as pyran, and a 5-membered hemiacetal ring is indicated as pyran from the original organic structure, which is furan and pyran, 6-membered, okay, with an oxygen in it, or 5-membered ring with an oxygen. We call it furan, with a 6-membered ring with an oxygen. We call this pyran. And so from there, we have the monosaccharides termed as furanose and pyranose. So they are used because the monosaccharides contains 5 and 6-membered rings correspond to the heterocyclic furan and pyran. These are organic compounds that has this structure. And if you look at our monosaccharide here, it's a 6-membered ring with an oxygen. So this is actually also named as pyranose. But since this is derived from glucose, we call this one as glucopyranose. And since we started with the D-glucose, we have the D-glucose pyranose. And since we have an OH downward, no, or yeah, the same position, you have the same position with the OH on the second carbon. So you have this an alpha D-glucopyranose. For this one, it's a glucopyranose, pyranose, D-glucopyranose, but the OH is up, constant is a beta. Okay, the short name for this is beta D-glucose. The short name for this is alpha D-glucose. Okay, but the name here, since it's a 6-membered ring with an oxygen, it's a pyranose, glucopyranose. The glucopyranose is still glucose. Okay. So again, furanose is a 5-membered cyclic hemiacetal form of a monosaccharide, and we call it pyranose for a monosaccharide having a 6-membered cyclic hemiacetal. So later we'll see how a furanose would look like. So in naming, because the alpha and beta form so because the alpha and beta forms of glucose are 6-membered cyclic hemiacetals, I have already mentioned, we call them as alpha D-glucopyranose and beta D-glucopyranose respectively. Or you simply call them as alpha D-glucose or beta D-glucose respectively. Draw the chair conformation for an alpha D-galactopyranose and beta D-galactopyranose. Okay. So if you remember in your organic chemistry, the rings, there are 2 ways for which you can write our cyclic ring for a 6-membered ring. One is you have the hexagonal structure. The other one is you have the chair structure. So the configuration of D-galactose differ from that of glucose at only carbon 4. Okay, so if you have 1, 2, 3, 4. Let's remember our galactose here. This is our glucose. You have down, up, down, down, up, down, down, or right, left, right, right. Sa atong galactose, you have right, left, left, carbon form. Instead of right, you have it left. So 2 OH to the right and 2 OH to the left. Galactose. For glucose, you have 3 OH on the right and 3 OH on the left. Okay. So let's go to the structure. You can have down, up, or right, left, left, down, or right, left, left, right, down, up, up, down. Okay, so this is our fifth carbon, and this is our OH. So when we draw the structure here, you have your OH that can attack the carbonyl carbon to form your O carbon, and the C-double bond O converted to an OH. So you have, when you write this other OH here, you have down, up, up, and the fifth carbon is used to form the anomeric carbon here. Okay, so this is our structure of for galactose here. And there's two ways to write our structure. One is you write in a chair. The second one is you write as this one. Okay, so if you write as this one, you will have, remember, down on the first carbon, right, left, left, dapat here. So, and for your galactose, so the fourth carbon, the OH is up, down. So that's the difference for galactose. So you can write the structure. Let's simplify first. Use this one. For the galactose, you'll get the same structure, but the OH is not written down here, but it's written up. Because when you write the structure, it's right, left, left, and then right. But this one is used to form anomeric carbon. Or when you write as this one, you have the right, you'll have the down, should be up should be the OH, and then you have this one. Are you following me? You can follow me. For you to follow, we'll have our okay, for your this is for your glucose. Okay, for your galactose, write the galactose. For your galactose on carbon 4, it's not written as this one. Okay, it's written the D-galactose. It's written, of course, the OH is not here on carbon 4. Baliktaran natin. Okay, the OH is very up. So we'll write as OH here. OH here. Okay, and then of course here is your hydrogen. So that is for the D galactose. And then of course your OH is on the right. So when we draw as this one, what you will get is on carbon 4, the OH should be, since we have down, right, left, up, it should be up, same here. So we'll erase this one for the galactose, and you will have this, your OH. You make sure that the bond is connected to oxygen and to hydrogen. So you have your hydrogen. So this is our galactose. Okay. So when it forms a bond, carbon 5, where you have your OH, it forms a hemiacetal. So the O can attack your carbon here, and you will get an OH, which can either be down or up. So you get an OR, O carbon, okay, can either be up and down. But of course, you have to remember that for a galactose, baliktad na siya. So it is so you have your na-record na ko ni.
Yes, ma'am.
Makita akong screen. So balik tayo, you have your OH. So balik tayo. So And then, of course, you have your hydrogen. Okay, so this is how our galactose looks like using the Howard projection, but we call this one not as glucopyranose, but alpha D-galactopyranose. You will have a name, an alpha.
Excuse me, ma'am.
Yes, maklaro?
Walay share screen.
Naklaro ba?
Yes, ma'am, klaro na.
Okay, so you notice that kopyahan na nato, no? Once you have already identified whether it's up, down, up, and the fifth carbon OH doesn't matter now if they're up and down, no? Because this one, the fifth one, should be down, but it's gonna form a hemiacetal. So you label that as 1. So you have your O. So the fifth carbon having the OH is used to form a hemiacetal here. Where you get your anomeric carbon, the suitable bond O is converted to an OH, COH. Okay. And you have there, and what happens is that you have your down, up here. You have your down, up, and then this OH is formed a ring here. So you will notice that on carbon 1, 2, 3, 4, notice that the OH is up, unlike your glucose where the OH is down here. Okay. So for us to name this one, this is a 6-membered ring. So this is a pyranose, but we don't call this as a glucopyranose, but we call this one as an alpha. Alpha. Alpha, kaya wala ko yung character ng alpha. Alpha D, galactopyranose. Okay, so you can start with pyranose, but what kind of pyranose is this? This is galactose. So you have galacto, and it's E pyranose, and since this is a D form, so you have the D galactopyranose, and since this is a down OH, you have your alpha D galactopyranose. So the short name for this is alpha D galactose. Okay, this one, this is not glucopyranose anymore, but this is already a galactopyranose. Okay, but in particular, you have your beta down. So you have this to be a beta. And the short name is of course, you have to use the character beta. The short name is beta galactose. It's easy to see. This is what we call as the Howard